Okay, hey there, mathletes. Welcome back. We're on section 1.2 or lesson 1.2 called functions. A function, but this is the definition. A function from set A to set B is a relation that assigns one element x in set A to exactly one element y in set B. Set A is called the domain or the set of inputs of whatever function it is we're talking about, say f, and set B contains the range or the set of outputs. So we'll start off with example number 1 here. Okay, so for example 1, mathletes, it says decide whether the relation represents y as a function of x. So here is y, our output, and here's x, the input. So we go through each one of these points and analyze them to see if we break any rules. So the first thing we notice right here is I have an input of 2 that maps to an 11, and an input of 2 that maps to a 10. So this piece right here, this violates our definition, because the 2 has to map to exactly 1, but not 2 different outputs. So I can't have a function. Think of a function like, say, f of x equals, I don't know, x plus 1. We'll keep it simple. I can never put a 2 in for this and sometimes get an 11, and put a 2 in and sometimes get an output of 10. So this is not a function. So we would just say, yes, not a function. All right, let's go look at part B. There's a little bit of a graph there. If you're following in your text, we're looking on page 17. So here is, let me get my pointer, 0 mapping to -1. 1 maps to 0, -1 maps to 0, 2 maps to 3, -2 maps to 3. So every one of the x inputs has a unique y output. So for that reason, we would say that yes, this is a function. And the other thing you might be remembering from Algebra 2 is if I connected these dots, I'd have a function that graphs something like this. And you learned something called the vertical line test. So that means, can I drop a vertical line and does it cross the red anywhere more than once? If it only crosses once, that is a test for a function. It's known as the vertical line test. So let's keep that in mind as we look at example number 2. Okay, so this is example 2, still on page 17 in your textbook. It says to determine whether the equation represents y as a function of x. So we'll look at them separately. I have A is given as x squared plus y equals 1, and B is given as -x plus y squared is equal to 1. So the first thing we want to do is, this leads us into function notation, or to solve for y. So I'm going to go ahead and solve this equation here for y by subtracting x squared on each side. So that would be y equals -x squared plus 1. So this would represent a function. And if we think of a graph, again, if I think of the graph -x squared plus 1, this is just a sketch. Do it in a different color. But you probably remember, hopefully remember, that that is a parabola that points down, and it's 1 unit above the x-axis. So, but when I go to draw a vertical line, I can drop vertical lines anywhere, and it only passes this red graph one time. So yes, this is a function. So any value I substitute for the x is going to give me a unique, not a unique, but it's going to have its own assigned y value. So inputs map to outputs. And again, the quick test that we learned last year, and that's why I'm bringing it up now, was the vertical line test. However, go over and look at number 2 here, part B rather. And if I solved this for, whoops, I want to stay the same color, if I solve this for y, I would start by moving x, add x on both sides, and then we take the square root of each side. So that's going to result in a plus or minus the square root of x plus 1. Make my plus and minus better there. So if I were to graph this, this is hopefully going on memory here for us, but we'll be doing lots more coming up. But x plus 1, square root of x plus 1 is, the parent function looks like, get my color back, it's going to sketch something like this. So that's for the positive piece, right? So maybe I should have color coded this. This is my positive piece. The negative piece is just going to be flipped across the x-axis, right? This is my x-axis, this is my y-axis. So let me do the negative piece. I'll do that in blue. We'll be red skinny here. And so that would look like this. So, and this can also be typed into a graphing calculator naturally. So if I were to drop a vertical line, how many times does that cross the graph? Well, it crosses up here, and it also crosses down here. So that tells us that this is not a function. Not a function. Fails the vertical line test. All right, before we hit example number 3, let's talk about function notation. Function notation. So right here, I wrote down function notation. So function notation just means that we're going to solve something for y. So a line that's in slope-intercept form is in functional form, but function notation is just a fancy way of saying change our y to f of x, or g of x, or h of x, or whatever that might be. But when you change your y to an f of x, you're using function notation. This is in function form. Let me write that down. Function form for y equals 3x plus 1, but f of x equals 3x plus 1 is called function notation. So that just means you're using the f of x. So that's as simple as that. So let's look at our example number 3 here. We're going to be given g of x, this is example 3, g of x is negative x squared plus 4x plus 1. So we can evaluate functions. So evaluating functions is a fancy way of saying, in the olden days, right, when you were in like pre-algebra, say, would be evaluate this expression when x equals 2. So g of x means we want x to be 2 up here. So the way we did that was we said, go ahead and substitute. I like to put the parentheses in place so we know where we're substituting. Plus, if you have to enter, if this were negative, I would have to have a negative sign in my parentheses. But this one's not negative, so this one's not too bad. So when we follow the order of operations, square this first, then apply the negative. So 2 squared is 4, so negative 4. So I'll write that down. Plus, multiply this, gives us an 8. And negative 4 plus 8 plus 1 is 5. So that means that g of 2 is 5. So my input is 2 and my output is 5. So, or we would say 2 maps to 5 using this function up here. All right, let's use this same function, but we'll check out part B. So part B gives us g of t. We're on page 18, by the way. So I'm going to do negative x squared plus 4 times x plus 1. And everywhere that we have an x is where we're going to put the t. So go ahead, we do that. Easy enough. So negative t squared plus 4t plus 1. And that is all. We don't have any like terms that we can add together here, so we're done with that one. And then part C, let me scooch over here. so that we can keep the function on the screen. So C wants us to find g of x plus 2. All right, these can be tricky. They can be tricky. But you just start with your function, which is right here, negative x squared plus 4x plus 1. And in place of this x, you're going to put x plus 2. So here's how it goes. I'm going to put my negative x squared plus 4x plus 1. So x plus 2 goes in here and also in here. So the first thing I'm going to do, remember order of operations, you have to square this. You have to FOIL this out, then apply the negative. So when we FOIL that out, it ends up being a negative x squared plus 4x plus 4. Make a better plus sign there. Plus 4 plus, and I can, this is a separate term, so I can distribute this right now. 4x plus 8, and I still have the plus 1 coming along for the ride. So now be careful here. This negative applies to each one of the terms inside the parentheses. So when I rewrite this without parentheses, everything inside the parentheses gets its sign changed. In this case, from plus to minus. I guess I could add those together, make that a 9. And let's see. Final evaluation here. Notice that we have negative 4x and positive 4x. So those add each other off. That adds up to 0. But when I go back to get the others, there's a negative x squared staring at us right here. And then we have negative 4 and positive 9. So we add those together. And we end up with, final answer, negative x squared plus 5. So when I substitute x plus 2 into this function, x plus 2 goes in place of x, and we just simplify it throughout, and it's not a number. We don't get a final number answer. We have an algebraic expression as our answer. All right, so stop this, rewind it, watch it as many times as you feel comfortable with, and plus we'll look at examples in class. What's up next? So yeah, example 4, I think I got cut off there. But this is about piecewise functions. Piecewise. And piece is not spelled like peace, like, you know, peace out. It's spelled piece is in pieces of a function. So a piecewise defined function usually will look like this. This one is called f of x, but it has two pieces. One piece they're giving us as x squared plus 1. Another piece is x minus 1. And then each piece tells you where in the domain it is defined for. So if I wanted to substitute a number less than 0, I would use this piece of the function. If we substitute a number greater than or equal to 0, we use this piece of the function. So part of the problem is find f of negative 1 and find the function when when x is 0. So f of negative 1, we look here, we see that negative 1 is less than 0. So that means we're going to use this function, x squared plus 1. So go ahead, parenthesis x squared plus 1. And here's where it is important to note that this is part of my base number. So that's negative 1 times negative 1. So negative 1 squared is, in this case, positive 1. So that would be 1 plus 1. In other words, 2. So f of negative 1 equals 2. Now let's go over here. F of 0, when x equals 0, now I have to look at which piece I'm going to use. When x is greater than or equal to 0, which it is, I use this function. So x minus 1 or 0 minus 1. So here's my x, put our parentheses in, and in place of that we'll put a 0. So x, let's see, 0 minus 1, negative 1. So f of 0 is negative 1. So depending on which piece up here we are using. You have to look at where it's defined before you decide which piece of the function we're going to use. And in class, I will show how to put this in a graphing calculator and set your parameters for that. Meanwhile, let's go on to the next example, number 5. For example 5, all we're doing is find the domain. So we're given a function, and this is called set notation, but it has 1, 2, 3, 4, 5 points. So my x-coordinate, that is my, let me undo that, that is my input. So the x-coordinate is the input. So the inputs are -3, -1, 0, 2, and 4. All of these input numbers are different, so it doesn't matter what the output numbers are. So like this one is the same as this one, but that's okay because it came from a different input. So for my domain, let me write that. This one, about the only way to write it is in set notation. So notice I'm just copying down the x coordinates from that list. And then my range, we use capital R for the range. For the range, you're looking at 0, 4, 2, 2, and -1. This is allowed for the range. They can come from different inputs. So 0, 4, 2, 2, and -1. So again, all I did was copy down 0, 4, 2, 2, -1. So that takes care of this one. But more importantly, what we're usually doing in algebra, pre-calc, calc, is we are looking at functions like this. And this happens to be a polynomial function. So one thing you have to remember is polynomial functions are always defined everywhere. So one of the easiest ways to do this is to say the domain is all reals, all real numbers. Another way of doing it is in interval notation. So we're familiar with that from Algebra 2. And the other way is to do it in set notation. Domain equals set notation. X, an element of the reals. Most students did not like that. That's a sloppy little brace there, sorry. But a lot of students don't like that. I did not like this when I was in school. I liked function notation, but words work also too. So you could just say whenever you see a polynomial function, all reals. Every real number can go in place of x. We're not restricted by anything there. All right, last but not least, let's look at part C of that. So here, we're given, this is called a rational function. Remember, rational means it comes from the word ratio, which is a fraction. So this is a rational function that's written as a ratio. So the only thing we're limited to here is we can't divide by 0. So x plus 5 cannot be equal to 0. So some students like to write this down, just say, well, x plus 5 does not equal 0. And solve that for x. X does not equal, cannot equal -5. Because if a -5 were put in here, you'd have -5 and +5. So you'd have 1 divided by 0, which is undefined. All right. From there, how do we write it? Well, you could write it using words. You could say all reals except -5, except -5. Or you could use, here the function or the interval notation gets a little wonky. You may or may not remember this from algebra, but you're doing a union of two open intervals. So everything from -infinity up to, but not including -5, in conjunction, united with everything from -5, but not including -5. That's why this is a parenthesis, not a bracket, up to infinity. And another way, since we're all different here, is to just say the domain, if I did it in set notation, is set x is an element of the reals such that x is not equal to -5. So any of these would be acceptable. You can use words, you can use interval notation, or you can use set notation. Like up here, words, interval notation, set notation. So that's a matter of personal preference for the most part. Unless a problem specifically states use interval notation, then you can state it however you like. All right, ready for another example. All right, so example number 6, page 21 in your text, is just find the domain. There's a picture of a sphere here, and it has the formula for the volume of a sphere. So they want to know the domain is what R values can we put in place of this. So this is a thinker, maybe, but R just has to be greater than 0. If I had a 0 in place of R, then I wouldn't have a sphere. And then I can't have negative numbers naturally. So I could just say all numbers, all reals, greater than 0. So that's with words. Or you could just say everything from 0 to infinity. And if this is interval notation again. If you're using interval notation, the reason this is a parenthesis and not a square bracket is because it cannot equal 0. It has to be greater than 0. But it's unbounded. It can go as however big you want the sphere to be. All right. And then just to stay like we've been staying, let me show you the set notation. R is an element of the reals such that R is greater than 0. And like I said, in my experience and me personally when I was in school, I did not like doing set notation. I preferred interval notation, or if it was easy as all numbers greater than 0, writing the words. So it's personal choice unless a problem is specifying use one of these forms over the other. So let's look at part B from example number 6. Part B is what is the what is the domain of this function? So we're looking at domains. So we notice that it has a square root. Can you take the square root of a negative number? And the answer is no, we can't. So we know that 4 minus 3x has to be greater than or equal to 0. Because I can take the square root of 0, right? It's just 0. So that's why I have greater than or equal to 0. So what we would do here is solve this for x, I guess. So I'll subtract 4 on each side, and then divide both sides by -3. So, be careful here. -4 divided by -3, that gives you 4/3. But because we divided by a negative, we have to reverse this inequality symbol. So that ends up being a less than or equal to. So you could say, again, using words, all reals such all reals less than or equal to 4/3. If you wanted to use interval notation, you'd say negative infinity up to and including, so we get a square bracket there. So this is one way of doing it. We did it in words, all reals less than or equal to 4/3. Here's interval notation. So 4/3 includes 4/3 and includes everything less than it. Or you could do set notation. So just again showing you all of these so that you can do whichever one is being asked for, such that x is less than or equal to 4/3. So 3 different ways to show those domains. All right, let's move on to number 7. All right, here's a PDF I made from a photo of the textbook, page 22, is, shrink it down a little. We are looking at just an example that uses, if you can see here, it has a piecewise function. So the number n in millions of employees in the construction industry in the United States increased in a linear pattern from 2003 to 2006. So from 2003, 2004, 2005, 2006. In 2007, the number dropped. Here's 2007 and 2008. So depending on if we're looking at 2003 to 2006, we'd look at this piece of the function. And if we were looking at 7 and 8, we'd look at this piece of the function. So t is the number of years since 2000, I suppose, because 3 is 2003 and 8 would be 2008. So from 2003 to 2006, we use this piece of the function right here. And when I substitute the 3 and the 4 and the 5 and the 6 into this function, this is the output that we get. And when we go to year 7 and 8, shrink that down a little bit, we want to know what this and this is. So we would be using this piece of the function, which is listed right here. So when I substitute 7 in place of t, we get 7.56. And when you substitute 8 in place of the t here, you get 7.14. 7.14. So millions of employees in the construction industry. So just kind of wanted to step you through that. That really wasn't an example to show, other than how to read that bar graph and how to use which piece of the function. All right, next up is example number 9. All right, so this is example number 9. It's talking about a baseball hit at a point 3 feet above the ground at a velocity of 100 feet per second at an angle of 45 degrees. And it shows the path of the ball and a calculator picture there. And this is the function that is given. So f of x, the height of the ball. You might remember this. This is off topic, but you remember h of t equals negative 16t squared plus vt plus s. You might not remember that. That's algebra 1, but this is h of t was the height as a function of time. So it included gravity. V was the initial velocity of the ball, and s was the initial position or the initial height of the ball. So if you kind of recall that, that's where this is coming from. So in any event, let's go ahead and look at this example. We want to know where f of x is, what's the height of the ball after it's 300 feet away. So it's showing a picture like this. And follows a parabolic arc. So when this ball is 300 feet away from where it went, how high is it? They want to know, what is this height? What is the y? So, or the f of x. Remember, f of x and y are the same, functional notation. So what we're going to do is go ahead and substitute 300, because on the x-axis, that's where this is 300 on the x-axis. So we want to find out what this height is. So substitute into the function. We have 300 squared plus 300 plus 3. So yeah, you can do this step by step or type this all into your calculator. If you were doing it step by step, you'd have what, 90,000. And let's see, what's 90,000 times 0.0032? Negative 0.0032. So I have that written down. It is negative 288. For those of you who just like to see it stepped out, plus 3. And then we add the 3 of those together and we get 15. So this ball is at this point, at this height, when you're 300 feet away from where it was shot, it is still 15 feet off the ground. All right, so that is hopefully helps you interpret that a little bit better. Then we have one last example, which has to do with something called the difference quotient. So let's look at that. Okay, last but not least, here we go. Example number 10. Let me write the 10 in here. So you are given a function that says if f of x equals x squared minus 4x plus 7, find f of x plus h minus f of x all over h. And this piece up here, this is called the difference quotient. That's why it says that on page 23. This becomes very important if you get into calculus. This is how we define, use a limit definition of that, finding something called a derivative. So if you're an 11th grader thinking of calculus, this will become really, really important. So all we have to do for now, though, is substitute, let's see, f of x plus h. I'm going to put x plus h in place of x, and then just keep it f of x here. So the way this rolls out is I got x squared minus 4 times x plus 7 minus my whole function. So put parentheses around this, because you're not just subtracting the first term, you're subtracting the whole function. So make sure you always put parentheses around this. All right, and that is all going to be over h. So I have x plus h and x plus h. So we have to just simplify here. So x plus h, so this is a binomial, so you have to FOIL it out naturally. So that becomes what? X squared plus 2xh plus h squared. Distribute here, minus 4x minus 4h plus 7. And then I'm going to distribute this negative 1. So minus x squared plus 4x minus 7. And that is still all over h. So I'll make my h here. All right, so a couple of nice things will always happen when you do these difference quotient problems. And one of those is your x squareds cancel, your x's cancel, and your constants cancel. They add off with each other, that is. So we end up with 2xh plus h squared minus 4h all over h. And if we factor an h out of the top, I'll do this step by step instead of just write the next thing. Right, so we factored an h out, right? Or undistributed it, if you want to think of it that way. H times 2x was 2xh. H times h was h squared. And h times minus 4 was minus 4h. And what happens there is these two h's cancel out. H divided by h is 1. So the last thing we have left is our answer, which is 2x minus h minus 4. And that is example number 10, and this completes our section 1.2. So watch this as often as you need to. Feel free to stop it, rewind it, and so on. And if you're watching it on YouTube, you can type comments in, and I can respond to them if needed. But anyway, thanks for watching. I'll see you again tomorrow.